Hi everyone. Today we'll be talking about one of the ways we scaled HashiCorp Cloud Platform, or HCP for short. My name's Alex, and I'll be joined with my colleague Janet, and we are engineers working on HCP. We focus on data planes and the control plane services which manage those data planes. So today we're going to cover what exactly is HCP, what aspect of HCP we're trying to scale, how we approach scale testing in general, how we identify bottlenecks within our scale testing, and how we iterate on solutions to those bottlenecks. So what exactly is HashiCorp Cloud Platform? HCP is our offering of fully managed HashiCorp products. We handle the operations and maintenance so you can focus on actually using our products to enhance yours. Today, we support Consul and Vault on AWS. For those unfamiliar with Consul and Vault, Consul offers service-based networking for dynamic cloud infrastructure. Vault allows you to secure, store, and control access to tokens, passwords, certificates, encryption keys for protecting secrets, and other sensitive data. Packer is our product for building automated machine images and will soon be available on HCP. We also have support for more cloud providers in the coming year. Check it all out at cloud.hashicorp.com. So when did HCP start? We started with a private beta in June of 2020 with support for Consul, and after that we added support for Vault. Who works on HCP? Today we have 100+ engineers across our platform, product, site reliability, and infrastructure teams. Once you add in product, design, managers, etc., the team is actually closer to 200 people. We're fully remote, as HashiCorp is, and we're spread across the United States, Canada, Germany, and the United Kingdom. And we're still growing. So there are two main components to HCP, the control plane and the data plane. For a control plane, we have a microservice architecture on top of the Hashi stack. For those unfamiliar with the Hashi stack, I'll get into that in the coming slides. From the control plane, you can initiate operations such as user management, product deployment, as well as monitoring and maintenance operations for your cluster. For the data plane, those are your resources that have been deployed on the cloud platform you chose, and they're managed by our engineering teams. To get more into the control plane, we have a microservice architecture on the Hashi stack, like I mentioned previously. And the Hashi stack is Nomad, Vault, Consul, and Terraform. So how we use Nomad? We use Nomad to orchestrate our containerized workloads on top of it. For Consul, we use it for service discovery and networking. For Vault, secrets, KV, PKI, transit encryption, and other secrets engine for access to cloud resources. We create all these things using Terraform, and we use Terraform to provision everything from our compute resources to our Vault mounts and everything in between. We also heavily leverage the integrations between the different HashiCorp products. One example of that is the Nomad Consul integration, which allows our services to easily register with Consul when they're deployed by Nomad. We also like to leverage the Nomad Vault integration to inject secrets into our containerized workloads. At a service level, we write all of our services in Go, and we use Cadence for our async workflows. Cadence is a workflow engine out of Uber and has been working great for our use case. A little bit about the data plane. So the data plane is comprised of the HCP product of your choice running in the cloud provider that you deploy to. In order to access a data plane, you peer your network to an HVN, which is a HashiCorp virtual network, where the, in this case, Vault resources reside. I mentioned Terraform before. On HCP, we use Terraform all the way down. Starting at the bottom, with our control plane infrastructure, we use Terraform to provision our Nomad client and server nodes, our networks, load balancers, databases, and everything else. Moving up a level, for our service config, we give each of our services a workspace in Terraform Cloud so we can easily manage state as well as control when Terraform applies or ran. Some of the types of resources that live in our service configuration are Vault transit keys, secrets backends, as well as Datadog monitors and SLO dashboards, so we can ensure that we're giving the highest level of reliability to our customers. Moving up another level, we have the data plane resources. This is all the cloud resources required to run a data plane. We'll focus on this in the coming slides. At the very top level, we have customers provisioning HCP resources using our public Terraform provider. Terraform providers allow you to programmatically create our HCP resources without going and clicking through the HCP UI. Focusing on that data plane Terraform aspect, we run Terraform to create cloud resources, and it's in the hot path of creating any data plane on HCP. So our original approach was horizontally scaled worker instances. And after ramping up 2 product offerings on HCP, we started to see a few downsides with this approach. So to go over that approach, each worker would pick up a Terraform workflow to run. It would fetch all of the Terraform files for that run from the calling service. It would then download the Terraform binary, as well as all of the provider binaries it needs to complete the Terraform run, and then it would actually run Terraform. A couple problems with this approach. The first problem is that weird things happen on the internet. Turns out that dynamically fetching binaries on each Terraform run increases latency. Downloading things from the internet is not instantaneous. Downloading things from the internet is also error prone. CDNs go down, DNS issues galore, blob storage buckets might have permission issues, etc. The second problem is that our Terraform runs are CPU bound and very bursty. Each worker could only handle a small amount of concurrent runs, so there's extra configuration involved to ensure that they weren't overloaded. Also, our service teams could consume all of the available workers in the case of a fleet-wide upgrade, a vault, or general high demand for the service. Scaling out these workers to handle peak bursts meant that many workers were idle most of the time, and this wasn't an effective use of cloud resources. Enter Nomad. So to solve these problems, we crafted an approach which leveraged Nomad's parameterized job feature, which allows us to shift the scheduling and compute away from worker instances and onto Nomad, where each Terraform run is its own Nomad job. This approach also allowed us to bake in our required Terraform files and the provider binaries that each run needs into our Docker image, which allows us to eliminate the dynamic nature of the previous approach. With this approach, we also added rate limiting and prioritized jobs so we can control the throughput of job dispatches, as well as allow mission-critical runs to be scheduled ahead of latency-agnostic background runs. How do we know it actually scales? Now we have this new approach to provisioning data planes, and we think it'll scale, but how do we know that for sure? We can't just release it into prod and cross our fingers. The first thing we do is start with a dashboard. I like to use the dashboard creation time to explore the metrics that we think we'll care about, and it helps us analyze our test results after we run our scale testing. The next step is to write some Terraform. I've used a custom test harness in the past, which works well, but Terraform gives you lots of those features out of the box. You can easily configure the number of resources you need to effectively stress your services, and you can use a provider that's public to your users to experience exactly what your customers see when they interact with your product. What if you don't have a provider for a Terraform provider? No problem. The Terraform providers team at HashiCorp has made scaffolding a custom provider a breeze. I helped work on the public HCP provider, and I can attest to the awesomeness of the plugin SDK. Before the public HCP provider, we had a private in-house internal provider that we would fetch from GitHub, and it was a lot harder to maintain than use the plugin SDK for scaffolding our provider. We also like to use the HCP provider for end-to-end tests during our CI pipeline, which end up gating our deployments. So let's say an end-to-end test fails in a lower environment, we can stop that deployment from making it to prod. The next step is to make a plan. Huge shout out to the SRE team on HCP for this one. We fill out an experiment template and document our goals following the scientific method, which allows us to easily chart our trajectory and set a goal of the amount of scale we're trying to achieve. Next step, once you have a plan, is run your tests. You can control the parallelism of Terraform with the parallelism flag, which easily allows you to stress your service as much as you need. Now, I'm going to hand it over to Janet.
All right, so now I'm going to talk about when we run the actual test. We have a framework, now what? So these are the basic steps that we use to run the iterations. We'd run the test, identify bottlenecks, and then come up with a solution and iterate on this. The scale test goals that we had this time were to stress the system until Nomad was overloaded. This was going to help us determine the optimal resource allocation. And then once we do make the changes to optimize for resource allocation and anything else that comes up, we could confirm that the high volume of concurrent Terraform runs were supported. So the actual test. What we ended up doing was we concurrently created HCP console clusters. Just a little background, HCP console clusters are run in a HashiCorp virtual network, and we acronym that as HVN. The cluster creations themselves, they use Terraform to provision cloud resources. So now I'm going to talk about the tests in our iterations. First, I'll just talk about the first test and how that went. And then I'll just talk about overall learnings from the rest of our iterations. So first test, cross your fingers because it's the first time you run it. When we run the tests, we're always using the Datadog dashboards, and this is just a screenshot of one portion of it. The circled graph on the bottom is a P99 console create deploy workflow latency graph. The blue line is the one that's just bumpy and has lots of peaks. The purple line you can see is kind of like straight through. The way that we have our workflows set up is we first do a create workflow and then we do a deploy workflow. So what we would have expected is for the create workflows and the deploy workflow lines to be pretty much lined up. What we saw is the create workflow was just having a lot of latency and it wasn't correlating to the deploy workflow. So we knew something was wrong. To try to look into why something was going wrong, we would look into the logs, look into tracing, and what happened in this first run was that we were blocked on an upstream workflow. So like I mentioned before, we have an HVN, and inside of the HVN, the HashiCorp virtual network, we have a console cluster running. The original way that we ran our tests the first time where we had created an HVN first outside of the scale test, and then decided to concurrently create like 100 clusters within that HVN. What ended up happening was that we were updating the HVN concurrently, and it was creating a block on that HVN write. So we had to change the way we ran our tests, and nothing works the first time. So we tested it again, and these are just the before and after graphs of the latency. The top graph is the same as a couple slides ago. In the after graph, you can see the purple and blue lines, which represent the create and deploy workflow latencies. They're just more aligned, and that's what we wanted, or that's what we expected. I just want to do a shout out to the custom metrics on the bottom. Those are our actual equations that we use to power these graphs. As you can see in the after graph, we still have latency increasing towards the end of our scale test. And I'm going to go into the reason why in a couple slides. So that was our first test. We reran it multiple times. And now I'm just going to talk about the highlights of what we learned. So the reason why a couple slides ago we had the increase in latency, it was because we successfully reached our goal of overloading Nomad. This graph, Nomad blocked evaluations. Basically what blocked evaluations mean in Nomad is that it was overloaded and it was no longer able to run any more jobs. This is using the Nomad integration Datadog graph. So now that we've reached our goal of overloading Nomad, we can tweak resource utilization in order to actually support that number of concurrent Terraform runs, and therefore eventually lead to 0 blocked evaluations. These two graphs here, the top one is the CPU usage, and as we mentioned before, Terraform runs are CPU bursty, so you can just kind of see like the graph, the lines come in super high, close to 800% of CPU allocated, sometimes comes back down, but the memory usage is pretty constant per job, so that just kind of signaled to us like we could optimize for memory usage, especially because we weren't using even 50% of what was allocated. Yeah, so these are the things that we did to optimize Nomad. We increased the Nomad client count. That would just mean there would be more compute resources, more memory. More compute equals more Terraform runs that can run concurrently. We also decreased the memory that was allocated per job just to better utilize our Nomad cluster. And in the future, we'd love to use Nomad's horizontal cluster autoscaler. We just didn't need it at the time, but totally in the future, if our traffic is looking more bursty, that's something we'd want to look into. Another learning that we had during these scale tests was to retry on rate limit errors. So this is just a screenshot of one of the console creation workflows failing, but under the hood, the reason why it was failing was because of rate limiting. We use third-party resources to provision our cloud resources, and rate limiting is just a really common way for a stable API to remain stable and reliable. What we ended up doing is we would catch specific rate limiting errors that we knew of, return a specific error code, and Cadence workflows make it super easy for you to retry based on different error codes. So all of that together allowed us to retry and then eventually succeed on our cluster creations. And to confirm success after all of these optimizations, the top right graph, it just shows like, yeah, in our last run, we didn't have any blocked evaluations after we were optimizing for our Nomad usage as well as rate limiting errors. The bottom graph is just, those two are both showing just kind of a before and after of optimizing memory usage. So in the after graph on the right, we see that we're hovering more close to 50% memory usage, which is a better use of our resources. Cool, so IRL, our learnings. Number 1, make sure your test is set up well. And I just think nothing works the first time, but also just doesn't hurt to double check everything. Totally normal. Number 2, retry everything. So rate limiting errors are super common. Try retrying on those for success. And then optimizing for resource utilization. Just making sure if your job is CPU bound or memory bound and kind of making the right call based on that. And in conclusion, at HashiCorp Cloud Platform, we created a solution for a high volume number of concurrent Terraform runs, and then we scale tested it to make sure that it was working as expected. And then we also used Datadog for a lot of our debugging and also confirming that a 300% increase in concurrent data plane provisioning was supported. And thank you so much. We super appreciate you all listening in and are happy to answer any questions. Thanks.